Good morning. Okay, it helps to have the microphone. So something. Good. Let me just quickly recapitulate what I did yesterday and then move on. So I started by explaining the Kondo model. And let me quickly recapitulate the Hamiltonian for you. So we started with this Hamiltonian. Which looks like this. So we normalize everything with respect to the Fermi velocity, and I explained that we have these chiral fermions, and we go to 1 + 1 dimensions. And so lambda was our Kondo coupling, and then there was this interaction between the spin and this electron current, which in spin space is written like this. And so as I argued, so there's an RG flow from a UV to an IR fixed point, both of which the theory is conformal. And so this was triggered by this operator, which is marginally relevant. And so first I discussed the case when we have an SU2 spin and one species of electron. And then we moved on to the case where we have SUN spin and K electrons. So is the microphone okay, or does it? Yeah, but maybe there was this. No, okay. If I'm here, yes, I hear it humming, but okay, fine. So then the only thing which I have to recapitulate from last time was this issue of critical over and under screening, where there was a typo in my formula, so I wanted to get this right. And I think there was just in the first formula, the factor of 2 was on the wrong side. So the critical screening is precisely when K is equal to 2 twice the impurity spin. And we can see that this first example fits in this category. So this equation was wrong yesterday. So if we have one species of electrons and the impurity spin is a half, then we get back to this case. And then the underscreening was when K is less than 2s impurity, which means there's a residual spin in the IR, and there's incomplete screening. And so this is the case. The overscreening is when K is bigger than 2s impurity. And then we get this non-Fermi liquid behavior, so where the electrons try to screen the spin, but then they overdo, and then somehow they try to compensate and so on. So it's a very complicated state and leads to a non-Fermi liquid. Okay, so this was just to recapitulate what I was doing yesterday, and so this equation really should read like this. All right, so then towards the end yesterday, I told you how to derive the gravity dual by some string considerations involving D3, D5, and D7 branes. And let me just write this table once more. So we had in these, these are our 10 dimensions. then, so we had n d3s in these directions, and then we have n7 d7 in these directions. So which preserves half of the supersymmetry. It leads to these to the electrons which we want, and then this d5 will now put the impurity, so it moves in time, but in none of the other spatial directions, and then it's here. And so this d5 embedding by itself would not break supersymmetry completely, but this combination of d7 and d5s actually does. And that's why we got this tachyon, which we actually want to get this holographic superconductor in ADS2. And so then eventually I ended up by deriving the holographic dictionary. And let me recap that quickly as well. So we have this electron current, J mu, which is psi dagger gamma mu psi. And so this is dual to an A mu gauge field in ADS3. Actually, it will be a transassignment field. And then we had this Abrikosov fermion charge density. So which was chi dagger chi, and so that was related to the size of the impurity representation, and so that was due to the time component of a Young-Mills gauge field in ADS2. And finally, we have this complex scalar which was O, and that was this product singlet of an electron field and one of these Abrikosov fermions at the impurity. And so that was dual to a complex scalar here, which actually arises as the tachyon from the D5, the strings between the D7 and the D5. Okay. So now, in principle, the gravity dual would arise from looking at all these branes in the ADS5 times S5 geometry. But as I explained, so this will be extremely complicated to solve, in particular because we don't know the value of the tachyon potential. So the strategy is now to actually solve something. We will write down a much simpler model, which nevertheless contains the essential features of this model. So the full string theory or supergravity is very complicated. And in particular, so the tachyon potential is not known, though in principle I think you can calculate it. And so the strategy is write down a simpler bottom-up model with the essential features. And so let me write this this model. So we restrict actually to 2 plus 1 dimensional models. So first we had, so on the field theory side, we have 1 plus 1 dimensional electrons coupled to the 0 plus 1 dimensional impurity. And now, so we couple this to an ADS3 BTZ black hole because we need finite temperature. So we look at the black hole in ADS3, and then we have this ADS2 slice inside this model. So, and of course, this entire dictionary which I wrote here, this should be somehow present in this model. Okay, so the action for this model, first, of course, we need an Einstein-Hilbert term for the gravity. So here's our Einstein-Hilbert, and because we want an ADS, we need a negative cosmological constant. Okay, that's for the gravity background, but then we also need a Chern-Simons gauge field which couples to this current. So that's already a matter content. And okay, so in what follows, we will restrict to the abelian case, which means there is only one flavor of electrons. You can do this with the non-abelian case too, but for simplicity today, let me not do it. And then, so this is the matter content in 2 plus 1 dimensions, but then we also have everything on the defect, and that will look like this. So first we have this abelian Young-Mills field. Oh, sorry. Okay. This is non-abelian, so this is the gauge field. Let me write in the non-abelian form. And then we have the complex scalar. And there's a covariant derivative, which I'm going to write down in a second. And so now for the potential, so in principle this comes from this tachyon potential, but now we just take a very simple model where we choose the potential to essentially be just a mass term. And so we choose this field to be exactly at the Breiten-Nonner-Friedman bound, which then determines the value of this mass. And this covariant derivative, so these indices run over time and the radial direction in this ADS2 space. So the covariant derivative looks like this. So it has a contribution from both. So we have two different gauge fields, one in 2 and one in 3 dimensions. And so they both contribute like this. Okay, so this is the model, and so now I'm going to discuss the physics of this. So we have to derive the equations of motion, and then solve them, and then draw some conclusions about the dual field theory. Okay, so I should say right away, but by just restricting to this 3-dimensional case, we have thrown away essentially the information about the field content of our field theory on the dual side. Remember, so that must be some kind of dimensional reduction of NX24 super Young-Mills, which is strongly coupled. So we will have these operators precisely in our dictionary, but what we don't know by studying this model is what is the glue which creates the interactions between these electrons, actually. We know, the only thing we know, they will be strongly coupled even before we put the defect, and this is a big difference to what we were doing beforehand. So the model previously had completely free electrons, and now we will have strongly interacting electrons, so they are strongly interacting even before I put this impurity. So they will be more like a Luttinger liquid and not like a Fermi liquid. But we don't know yet exactly which Luttinger liquid we are looking at. That would be actually something, I think it's possible to find out, the parameters which characterize this model, but this is something which needs still to be done in the future.
Sorry?
Yeah?
The non-abelian gauge field.
Yeah.
What is the gauge group? Because I have lost.
So the point was that it's related to. Okay, so it's related. So near the boundary, this gives you the charge density. So this gives you. This counts the number of degrees of freedom in the defect. But by itself, I think it's going to be an abelian gauge field, which comes from this spurious symmetry which we get from introducing these Abrikosov slave fermions. Yes. Okay. Good. But I'm going to do all this now. I'm going to write down the equations of motion, and then we look at the boundary behavior. We now use the standard machinery of ADS-CFT applied to this particular model. And now, this model doesn't look too complicated, but okay, as you can see, it takes quite a number of thoughts and input to actually write down this model to characterize this quantum model. Okay, now let's solve it. Yeah.
With this choice of K, you will always be in the understream.
This is an excellent question. I will come back to this question. So the thing is, okay, so the true answer is, as we will see in a minute, because the electrons are now strongly coupled, we cannot use the simple argument which I was doing before. The simple argument I was doing before was for the free electrons, where then you can just form simple tensor products. But now, since we have these strongly coupled electrons, this is no longer possible. And one of the unsolved questions of our model is exactly whether it is overscreened, underscreened, or critically screened. And I will come back to this point in about 5 minutes when I write down the solutions to the equation of motion. But this is a very good question, and the true answer is we don't know yet, and we should work this out. But I tell you why it's not so easy to do. Okay. So now we just write down the equations of motion. Okay. So Z is the radial variable in this. Okay. So first of all, I'm going to do everything in a pro approximation. So the metric will be the BTC black hole. So let me write the metric. So that, and this function h is this done. Okay, then we need plus dx squared. And this is just 1 over minus z squared over zh squared, where zh gives you the horizon of the black hole. Okay, so, and essentially this Chern-Simons field will be non-dynamical, and you will see that the non-trivial equations of motion to solve are those for the fields exactly at the defect on this ADS2 subspace. Okay, and then another thing I'm going to do is this complex scalar field I'm going to write as a modulus and a phase, and you can show that essentially the phase decouples, and you can just talk about the modulus of this field. Okay, so I should write consistent. So this is my phi. Sometimes I write phi like this. So if you see a phi like this, it will be the same as this one. Okay, so it's the modulus of this complex scalar. And so the really important equations are now the following. So G is this BTZ metric. And the last one is the one for this modulus. So this is the equation for this 2D Young-Mills field. And here there's a mass term. From this mass term we get a contribution. Okay, so and then essentially you see this AX will decouple, so the field in 2+1 is non-dynamical, but so you see it has a non-trivial source from this defect, which is this term here. So this will actually give you later on, will give you the, but it will be responsible for the phase shift, which we were discussing yesterday. Okay, so then the important set of equations are these on this 1+1 dimensional subspace of the BTZ black hole. So the dynamics is determined by the equations for AT and phi on the 1+1 dimensional subspace of the BTZ black hole. And so it's spanned by z, which is the radial coordinate. And t, which is time, so it's dual to this 0 plus 1 dimensional defect. Okay, so when you do ADS-CFT, what you have to do is to solve this, but then what is very important is to look at the boundary behavior of your equations to determine the source and the web of your operators. And so this we also do here. So as I mentioned yesterday, there will be a phase transition. So, and especially this phi, there will be a high temperature phase where this phi is 0, and there will be a low temperature phase where it's non-zero, and there will be a second order mean field phase transition between these two. But let's first, so there will be the unscreened phase is when phi is 0, and in the screened phase, there will be a condensate. So we will. All right. So at high temperatures, we will have a solution where phi is equal to 0. And then you can straightforwardly solve the asymptotic behavior of this AT field. And it's going to be, as I said, Q over Z plus mu near the boundary. Where, okay, so the condensate, or the expectation value, I should say, of our charge density will be related to the, so previously we said that this is actually, there's this constraint which sets this to Q, which was the number of boxes in the Young tableau of the spin representation. And so then from the prefactor, okay, now you can't see my model anymore. Okay. Anyway, so there was a factor, so there's this factor n arises from the prefactors which I put into the action. And so this Q, this asymptotic behavior, will involve the number of boxes in the Young tableau and n in this fashion. Okay, and and this mu will be the chemical potential for this U1 symmetry. For this spurious U1 of the Abicosov fermions, this chies. Okay, so very good, very nice. So this means now what I've told you is what happens when we are at this UV fixed point. Okay, as you can see, obviously the more interesting solution will happen when this phi is not equal to 0. And so now we need to push our model out of this fixed point. And we know how this happens. This is by switching on this Kondo interaction. And yesterday I told you, so obviously in ADS-CFT we are always in the large N limit, so we have this SUN spin group. And N goes to infinity. And so then I told you that we can rewrite this as lambda delta of x O times O dagger, and this was this double trace operator. And O, as you by now remember, is psi dagger chi. Okay, so now this means we have to look at an RG flow which is generated by this double trace operator. But there is a rule of how to do this in ADS-CFT, which has been around for quite a while. Okay, so then this means for generating the Kondo flow, the RG flow, we need to turn on the double trace operator O dagger. Okay, and let me tell you how to do this. And so first noting, so we choose, so obviously this will somehow be related to the phi field. Okay, I told you that phi itself is dual to essentially to one of the O's, so how do we get this double trace? So first of all, we choose phi to be at the Breitenmüller-Friedmann bound. So this is just at the margin to being unstable. And this means that m squared, so in anti-de Sitter spaces, the mass squares can be slightly negative and there's still stability. This is this very famous result of Breitenmüller and Friedmann. And we just go at the edge of this region of stability. So this Q enters, if you look at the equations of motion, if you from the AT, as I showed you, and then so we have an effective mass, and so this is precisely this value which we should take at this Breitenmüller-Friedmann bound. All right, so now let us look at the asymptotic behavior of the field phi. So the asymptotic behavior of phi near the boundary so here you see it, so sorry, phi. So there's two coefficients, alpha and beta, and because everything is in such a low dimension, there will be logarithms appearing here, actually. So this is a UV cutoff, this lambda, and there's a coefficient alpha, so this is the first term, and then the second term will be beta times square root of this z variable. Okay, so this is what you obtain as the asymptotic solution, and as you know, there's alpha and beta will related to the VEV and the source. Are there any questions? It's okay? Okay, so this is important now. From this we can determine the VEV, the source, and this double trace coupling. Okay, and this is actually a result by Witten already from 2001, where he worked out how to determine this double trace term from the boundary expansion. keep putting this wiping stuff in. Okay, so I did it the wrong way around now. Sorry. Okay, so now we use this result of Witten from 2001. So the paper is HEP TH 01-12-258. This is very easy to follow and understand, so let me just quote the result. So, by looking at the source on the web and so the effective action which you define for those, we obtain a double trace coupling by imposing a linear relation between these alpha and beta. I hope you can still see alpha and beta, so these are these. Okay, so here's my linear relation. And so this kappa will now be the coupling of the double trace operator. Okay, so
One question. When you choose the screen dimension of the operator, is this consistent with what we had like yesterday, that this OS dimension 1/2?
Yes, exactly. No, okay. So, very good question. So at the beginning, I showed you this dictionary which we derived yesterday. This model is based on this dictionary. So yes,
it's the same.
It's the same. Okay. I mean, this is the only ingredient which we can keep easy. Yeah. No, very good question. This whole model is built to be the simplest model which respects all this dictionary which I derived yesterday. So we respect this dictionary, but what the information we lose is how the electrons interact with each other, apart from interacting with the impurity. Okay, yeah.
Sorry, but whether the BF bound is satisfied or not depends on that dimension of the operator, but why do you say that you need to choose something about phi to saturate the bound? So
No, okay.
What do you choose?
Okay, so I have to choose the potential the correct way.
Okay.
The dictionary is given first. And so the problem is I wasn't able to derive this potential from this tachyon. So the clean way would to calculate the potential from this tachyon.
Okay.
This I cannot do, so I take the information I have about this phi to fix the simplest property of this.
The mass and then
Yes. Yeah.
Okay.
So I know something about phi and then fix the potential, not the other way around.
Okay.
Good question. Yeah. Okay. So then also we take in very low dimensions, there's a choice whether alpha and beta are the VEF or the source. So in this case, we will take beta to be proportional to the VEF of this operator. And then obviously alpha will be proportional to the source. Okay. Good. So now the next step is that, so now we can have some information about this kappa, because now we can say that our field phi has to be invariant under, so it's a physical field, so changes of the renormalization scale. So, and if the total field changes, this means that these coefficients alpha, kappa, and beta are going to change. This implies, so if phi is invariant, this implies that kappa is going to vary, and kappa is going to be kappa naught divided by 1 plus kappa naught. So this is the value in the phi uv, if you want, and then there will be a log of lambda naught over lambda. So where lambda is the new value of the renormalization scale. Okay, so this is all in this paper by Witten, which I mentioned, and so what we did is to translate this approach to our model, and in particular, we have to look at the model at finite temperature. So then at finite temperature, we obtain the analogous result, so just trading RG scale for the temperature, essentially. And then, so we have a kappa at finite temperature, so, and this is the original kappa divided by 1 plus kappa log lambda, so which is the UV scale times ZH, which is the value of the radial cone at the horizon. And then obviously, because we have a black hole, so there's a Hawking temperature, and we know that ZH is equal to 1 over 2 pi t. Okay, who has seen this equation before? And when? Well, the answer is yesterday. Yeah, okay, yeah. Yeah, okay, so very good. This equation was on the blackboard yesterday when I was talking about the field theory Kondo model, okay? Now, this is the gravity Kondo model, but we get exactly the same behavior. So we have a Kondo temperature at which this coupling diverges, okay? So this is super beautiful, okay? I did a gravity calculation and I reproduced this field theory calculation. So the field theory calculation was obtained by summing Feynman diagrams to all orders. Here we just solve an equation of motion, okay, in the gravity theory. So let me just plot this. So, okay, so first let me write a sentence with an exclamation mark because this is nice. So the Kondo temperature which now is Tk equal to 1 over 2 pi lambda e to the 1 over kappa, at which the Kondo coupling diverges. And I can just now plot, let me just plot this function. Okay, so the function looks like this. If on this axis we have 2 pi t over lambda, and here we have kappa t. So now you can't see anything. Okay. Essentially, okay, so this is where essentially we will have tk in these units, and then so this function will do something like this. Okay. Good. Okay, so now we discussed the boundary behavior. So now, of course, we have to solve the full equations of motion, but unfortunately this can't be done analytically, so we have to do it numerically. Yeah?
What about this? I mean, this is the profile of the scale field.
Yes.
Then what happens to this profile when we get to this Kondo temperature? For the solution, right? It diverges, or there's things that cancel?
No, I'm about to tell you this. Let me. Okay. I will answer the question in about 1 minute. Okay. So for physical results. We solve the equations of motion numerically. And we find, so this is the answer to your question, we find mean field phase transition at a temperature Tc. So I think I mentioned that at the very beginning yesterday. So this is roughly Tk, but it's a little smaller. So this can be calculated. So Tc can be calculated or has been calculated analytically. So this involves some harmonic numbers and so on, and it's a bit complicated to discuss how to do this, but so you can calculate this analytically. And the result is that it's of the same order, but it's a little less than this. And this is good because then you can do your numerics essentially in this branch. Okay, so you start with so Tc is roughly there. Okay, so then you can start here. And then you follow this line and see what happens. And the result is the following. So here's the result. So here let me plot the condensate, which is essentially given by this coefficient beta in the expansion of the scalar. And here I plot T over Tc. So this is where 1 is. And then we see a beautiful mean field phase transition, which does something like this. Okay, so here there's a square root behavior. Okay, it almost doesn't look like a function. I mean, it should be a function. Okay. Okay, so if we zoom into this region, so we see this mean field. And so we have exactly the structure which we want to have. Remember yesterday I told you what happens at large n in the field theory, and now our gravity model reproduces exactly this. So at high temperatures, this is the unscreened phase, but in the screen phase now we have a condensate for this operator, and remember this operator was this. So, and this really gives us our screening because the electrons somehow combine with these, they form these singlets with these Abrikoso fermions, and this means that the impurity degrees of freedom, they are kind of hidden, or so this is just the essence of this word, the screening. Okay, so it's this condensation for this operator, and we do see this in our model. So this is a very nice success. Okay, if you're interested in model, I can also tell you other things which are maybe not quite as nice, and what is not quite as nice is the behavior here. Okay, I've just drawn here that it really goes to a constant, but I think this is a little over-optimistic, and also certainly at very low temperatures it's always very hard to do numerics. And now, I mean, since we've been working on this for a couple of years, I mean, we have the feeling that this is actually going to diverge. It's going to be nice here, but at the very end, something really nasty happens. And this, of course, happens because our potential doesn't have any quartic term. We have just this m phi squared. If we were to add a phi to the fourth term to get a really beautiful Mexican hat potential, then I think we could stabilize this. And okay, so this is something to do for the future if somebody's interested. But I mean, certainly in all this region until very, very close to t equals to 0, we get exactly what we expect from the large N field theory discussion. So this is a very nice example a new example of how gauge gravity duality works. So it's interesting by itself. Okay, so now let me tell you a little bit about what are the physical properties of this model. Okay, so for the screening, I mean, okay, the formulation of the condensate is already some indication of the screening. Then I should also say that we calculated the free energy for the solution and found that it is less than in the normal phase, so we can really say that this is the stable solution. This is always something very important to check if you look at phase transitions. And in fact, so what we would like to see is that somehow these degrees of freedom at the impurity, which were given by these Q boxes of the Young tableau, are actually eaten up. Okay, so somebody was asking earlier, do we have over or under screening? Okay, let me tell you a little bit about this now. Okay, so can we we already have some indication that the screening happens, and can we make this more precise? So, and in fact, we can use the following fact that the electric flux of this field AT of Z at the boundary encodes information about the impurity spin representation because if you calculate precisely this quantity, which I'm writing right here, so this is your electric flux. So it's the ZT component of the field strength of this gauge field AT. Then you can actually show that if phi is switched off, this is actually equal to this Q, which counts your number of boxes in the representation. Now this looks very complicated, but this I can reduce, and this is just AT prime of Z. Okay, so in the normal phase, so this flux precisely encodes the size of the impurity representation. And now, of course, the idea is if we calculate this now at the horizon and then lower the temperature, we should see this decreasing because, due to the screening, some of these degrees of freedom will be eaten up. Okay, and this is precisely what happens. Okay. So when phi is equal to 0, this is constant from the boundary to the horizon. So when we're in this condensed phase, so when T is less than Tc, the non-trivial phi draws electric charge away from this AT of Z, reducing the electric flux at the horizon. And this reducing is precisely corresponds to the screening. So the effective number of degrees of freedom is reduced. Oh, I keep using this stuff for what is probably on the other backbone. Sorry about this. Okay, so we can calculate this electric flux at the horizon, and then we lower the temperature, and we see that it decreases. So, which again tells us that we have less degrees of freedom. Okay, so we see that the effective number of degrees of freedom is reduced. So, and then let me just plot this. So here, if here it is T over Tc, and here is this flux, which is A prime index T at Z equal to the horizon, so this is at the horizon. And then, okay, we see beautifully that this decreases, something like this. And then we have the same problem as before, that our numerics is not really good enough to say exactly what happens here. Okay, so according to the rules I told you yesterday, we have one flavor and SUN spin, so it should be an underscreened system. But I'm not so sure if this is the case, because I'm not so sure this argument really applies when in the strongly coupled electron system. So, and then there's also this problem of the stability of the IR fixed point. So I think this is an unsolved question which remains to the future, but certainly I think what needs to be done is to add this quartic potential and then reanalyze more precisely this region. And another thing which would be very interesting to do is to really look at the Luttinger parameters of the dual field theory, and I'm sure something can be done about calculating them, and then we can solve your question about the kind of the screening. Okay, time's almost up, but let me mention two more facts. So one, of course, what happens to the resistivity? Okay, so according to this CFT approach to the quantum model, this can be calculated from the so-called leading irrelevant operator analysis, where we perturb about the IR fixed point using the leading irrelevant operator. And this we can also do in this gravity picture, and I'll tell you the result in a second. But this also motivated us to actually calculate the two-point functions, so the retarded and advanced Green's functions for this model. This is what I'm going to tell you about this afternoon. And so let me just quickly say, so okay, yesterday I said this important fact was this logarithmic rise, but this we don't see here. Here we get something, we get t to some power of a real number. And this is not totally unheard of, so it's and this is actually consistent with the fact that our electrons are strongly coupled and not free, so it's similar to a Luttinger liquid behavior. So a Luttinger liquid means it's a non-Fermi liquid in 1 + 1 dimensions. Okay, so we do get a behavior which somehow reflects the strong coupling nature of our electrons. Okay, now more physics we can do with this model. I mean, okay, I think you should appreciate this model as a very beautiful example of a gravity dual for some field theory. And, but there's more useful things which we can do, and I will tell you about this afternoon. Most importantly, we can calculate the entanglement entropy. And so this, of course, requires including the back reaction. So probably you have all heard of this famous result of Ryo and Takayanagi, where they map the entanglement entropy to a minimal surface in the dual geometry. And of course, at the moment, our defects fields do not influence the surrounding geometry, which is just a BTZ black hole. So this means this minimal surface would be the same for all values of the defect fields, and then, of course, we don't see anything. But we can actually calculate in a simple model the back reaction, and then what is very nice, we can actually compare our result to some previous field theory results and get exactly the same. So this is what I'm going to show you this afternoon. Another interesting thing we can do is quenches, which is switch on in this Kondo coupling kappa at some t is equal to t0. So previously, for instance, you are in the unscreened phase, and then you switch this interaction on, and then the system will go to the new phase. And so this turns out will be, so the behavior will be determined by the quasi-normal modes, so which are the complex eigenfrequencies of the fluctuations about the background. So these are the complex fluctuation eigenfrequencies. And so finally, then what we can do is calculate advanced and retarded Green's functions, also using standard techniques in ADS-CFT. And this gives us some very interesting information about the resonance structure of these, and this is what I'm going to tell you about this afternoon. So thank you very much. I mean, let me emphasize again, I mean, so the motivation for doing this, I mean, one side is you have this really beautiful example where you show how to construct a gravity dual for some field theory. And then on the other hand, now there will be really quite a lot of applications also in condensed matter physics, which is also interesting. Everybody wants coffee.
Time for coffee, let's thank.